Major discoveries about the development of the multiverse continue to unfold, thanks to the James Webb Space Telescope JWST. One of the most intriguing revelations involves a mysterious planet in the habitable zone of its star, Proxima Centauri. This exoplanet, known as Proxima b, has been described as Earth's cousin, making it far more than just another rocky world in space. Recently, JWST has captured its finest image yet, providing astounding details about this potentially habitable exoplanet. What secrets has the JWST uncovered about Proxima b? Let's dive into the fascinating discoveries. The James Webb Space Telescope is equipped with highly advanced and sensitive instruments that allow it to probe the early history of the universe, shedding light on the formation of galaxies, stars, planets, and potentially even life itself. Using infrared imaging, the JWST enables astronomers to look back billions of years, offering a glimpse into how galaxies evolved over cosmic time. These infrared images reveal aspects of the universe invisible to the human eye. The telescope's capabilities depend on how it is utilized, similar to applying filters to images on a smartphone camera, but on a far more sophisticated level. By isolating specific wavelengths of light, scientists can analyze various celestial objects in incredible detail. This technology not only helps in studying the cosmos, but also in investigating the atmospheres of exoplanets for potential signs of extraterrestrial life. One of the most significant breakthroughs in astronomy has been JWST's discovery of far more mass in the universe than previously thought, particularly in massive galaxies. Alpha Centauri, the closest star system to Earth, lies about 4.25 light-years away, meaning our view of it is always for years out of date. After years of searching for gravitational disturbances hinting at an orbiting planet, astronomers finally identified Proxima b. This exoplanet orbits Proxima Centauri, a red dwarf star loosely associated with the Alpha Centauri system, at a distance of just 7.3 million kilometers. Although this is less than 5% of the distance between Earth and the Sun, Proxima Centauri emits far less energy than our Sun, creating a unique environment. If observed from the planet's surface, its parent star would appear as a massive, dim red orb quite different from the bright sun seen from Earth. Despite its close orbit, Proxima b is located in the habitable zone of its star, meaning its surface temperature could support liquid water. However, that doesn't mean it's an ideal second Earth. The planet's rocky composition, similar mass to Earth, and moderate climate conditions make it an intriguing candidate for potential life. Yet, Proxima b presents numerous challenges. Its surface temperature is uncertain, ranging anywhere from -33 degrees Celsius to scorching hundreds of degrees, depending on location. Moreover, the planet is likely tidally locked, meaning one side is in constant daylight, while the other remains in perpetual darkness. This extreme environment could make sustaining life difficult. Water on Proxima b faces another challenge. If it is too close to the star, intense radiation will boil it away. If too far, it will freeze. Astronomers are particularly focused on planets like Proxima b because they represent the best chances of hosting life as we understand it. However, life on this world would face harsh conditions. Red dwarf stars, like Proxima Centauri, have smaller nuclear fusion cores compared to stars like our Sun. This results in extreme surface turbulence and significantly stronger magnetic fields. Such violent stellar activity could make Proxima b an inhospitable place, but its potential for hosting life remains a fascinating subject of study. Astronomers continue to monitor Proxima b for new insights, hoping that further observations will reveal more about its atmosphere, surface conditions, and potential habitability. While it may not be a perfect twin of Earth, its discovery has deepened our understanding of exoplanets and the diverse environments that exist beyond our solar system. With the James Webb Space Telescope pushing the boundaries of exploration, who knows what other incredible discoveries await us in the vastness of space. The resultant powerful high-energy radiation and particle bursts into the surrounding system are made possible by those strong magnetic fields. This is not a significant issue when you are sufficiently far from a star, yet the habitable zones of stars like Proxima Centauri are much closer since they aren't nearly as bright as the Sun. It's close enough that the phrase habitable might be overused. Although scientists were already aware that life on Proxima b would be extremely challenging, they had to rely on studies of nearby stars, because they were unaware of the precise magnetic field conditions around Proxima Centauri. A new study used high-resolution magnetic field maps of Proxima Centauri to create a model of the star's solar wind. They discovered that the situation is just as dire as anticipated. After receiving more reliable information, scientists found that Proxima b receives roughly 1,000 times as much solar wind radiation as Earth does. In fact, a Proxima Centauri flare in April 2021 was 100 times more powerful than any sun-related flare ever observed. Any life on the planets close to the star would be at risk from such flares. It is doubtful that humans could ever survive on Proxima b without specialized shelter. Despite these challenges, many individuals remain optimistic about finding life in the Alpha Centauri system. In late 2020, this hope was strengthened by the discovery of a peculiar signal that appeared to originate from this system. Although the signal was actually received in April 2019, it took over a year for anyone to notice it. What made the signal intriguing was that it was detected at 982.2 MHz, an unusual frequency that is not typically occupied by Earth-based satellites or spacecraft. This anomaly increased researchers' interest in determining the signal's origin. While the source remains unknown, experts cautioned that it most likely was not from an alien civilization, suggesting it was probably caused by a piece of manufactured equipment. However, some continue to hope that this signal might be evidence of intelligent life. What do you think? Would you like to encounter aliens from the nearest planet to our solar system? Or perhaps, if you ever make it to Proxima Centauri, you would be on your own. But how can humanity even reach the Proxima Centauri system? Even with our fastest spacecraft, it would take hundreds of years to approach the closest stars. To allow scientists who initiate a mission to live long enough to see the results, Breakthrough Initiatives has been exploring ways to reduce this journey to just a few decades. A recent study published in the Journal of the Optical Society of America acknowledges the challenges of interstellar travel, but suggests that some of them might be overcome using current technology. One of the biggest difficulties in space travel is accelerating an object as its mass increases, especially as it nears the speed of light. This presents a major challenge for any spacecraft carrying its own fuel. Alpha Centauri is the closest star system to Earth, but using current propulsion methods, a journey there would take around 6,000 years. One potential solution is laser propulsion, an idea that has been around for some time but is now being seriously considered by Breakthrough Starshot. However, this approach presents several difficulties. As Banju Tongao, a scientist working on the project, explains, Earth's atmosphere significantly affects incoming light, causing stars to twinkle. This same atmospheric distortion could interfere with laser propulsion, disrupting the laser's focus on the spacecraft. Some researchers have proposed launching the laser system from the moon to avoid this issue, but the cost would be astronomical. Instead, the study's lead author, Banju Tongao, suggests using adaptive optics technology used in telescopes to correct for atmospheric distortion. In this case, small lasers mounted on satellites could assess atmospheric effects in real time, allowing powerful ground-based lasers to adjust and maintain a tight focus on the spacecraft. To propel a spacecraft toward Alpha Centauri, the lasers would need to generate an immense 100 gigawatt of power at any given time, about 1/4 of the total electricity consumption of the United States. However, Banju Tongao and his colleague Dr. Paul Sibley argue that this power only needs to be sustained for 10 minutes. The idea is to use a battery or a supercapacitor system that stores energy over several days before unleashing it all at once. A network of 100 million lasers would disperse the energy across a square kilometer area, ensuring that when the lasers switch off, the spacecraft would be traveling at approximately 20% of the speed of light. At this velocity, it could reach Alpha Centauri in about 22 years, provided that the Sun's gravity and interstellar medium do not slow it down significantly. However, once it arrives, it would take another 4 years for its transmissions to reach Earth. One of the biggest remaining challenges is preventing the probe from melting under the intense energy of the laser beams. To mitigate this, the spacecraft's mirror would need to be nearly perfect, reflecting 99% of the incoming light, while also doubling the momentum transfer and reducing heat buildup. If successful, the probe could traverse the Alpha Centauri system in just a few days, though it may never get very close to any of its planets. The advantage of this method is that, once the launch system is established, additional probes could be sent at relatively low cost. With a fleet of such probes, humanity could get fleeting but valuable glimpses of Earth-like planets beyond our solar system.